Okay then, so let's go back to this idea about internalizing composition. All right, so um, we want to really try and understand how it is that this f to the power of a thing works. So um, f to the power of a is defined to be the transpose of f after EAB. Okay, but we want to gain some intuition about how it's working. So let's remember this thing about the names of arrows. So say we have an arrow H from A to B. Well, that's equivalent to an arrow from 1 times A to B. And taking the transpose of it, we get the so-called name of H, H in quotes, which is really the transpose of H after P2. I mean, H after P2 is really this kind of equivalent way to state H, but we're kind of almost redundantly multiplying by the terminal object at the start. So it's sort of like saying, oh, well, instead of having a function from a set to a set, I've got a function from a constant paired with a set to a set. It doesn't really make much difference. But anyway, this is the name of H, okay? And I mean, really, when we sort of do the transpose of the name of H, we just get H P2, which is like almost equivalent to H, okay? So there we are. So anyway, we've seen this diagram before, and it's really the diagram which proves this formula here that f to the power of a operating on the name of H gives the name of FH, okay? But I want to just go through some sort of intuition behind this. So let's just think about firstly how transpose works in general. So suppose we have an arrow S from Z times X to Y. Well, the transpose is going to go from Z to Y to the power of X. And how can we think about how this transpose works on some member of Z in set? Well, when it works on some member W of Z, what it gives us is this sort of ready to evaluate function, which is ready to take in an X dash and give out S of X dash comma W. Now we can write this in lambda style notation. You see it's just similar, but we're just using this lambda X dash dot instead of this X dash maps to. I kind of prefer this because I've played around quite a bit with Scheme and Haskell and things like that, which have this kind of lambda syntax. But these are just two equivalent ways to say the same thing, really. Well, we can think of them as such. So then how are we to think about this situation? Like, I mean, think about this when we're here, for example, and we're going along this arrow. I mean, this is really the complicated part. So, I mean, what have we got put in here already? Well, if we're doing this kind of stuff, let's say in set, then what we're going to be doing along this arrow, we're going to have some name of H, which is going to be a member of this set B to the power of A. So we're going to have a sort of name of some function, and we're also going to have some element little a of this set capital A. And then when we do this function here, we leave the little a alone, but we change H quotes to F of A H quotes. So the real question is, how does f of a work on h quotes? Well, we can really take the bull by the horns here and just write out the sort of full expression for f to the power of a, and it's f EAB transposed working on h quotes. So the question is, how does this work? Well, if we simply use this sort of formula here, we can say, okay, what have we got here? We've got the transpose of something operating on h quotes. So if we just look at this form, that means that, well, this thing that we're taking a transpose of ought to take two inputs, just like S took an X dash whoops, got those the wrong way around. Doesn't make much difference really for understanding, but yeah, okay, so let's carry on. So the question is, what happens when we have the transpose of something operating on something? So here we have a transpose of FEAB operating on H quotes. But I mean, here we have a kind of more general situation where we have this S, which takes in two inputs, a W from Z and a little x from X, and it outputs something from Y. So what's it mean to do the transpose of that, as in S cap, on some W from Z? Well, what we get is lambda x dash dot S of W comma x dash. So all this does is it takes this S and leaves the W fixed, but it's ready to take in a general kind of x dash and feed it into the second entry of our thingamajig. So okay, we can do similar here. So the question then is, this thing that we're taking a transpose of, is this some sort of a function which takes two inputs? Well, yeah, we can see it is here. So it's going to take in a h dash and an element of a. And so we look at this formula and we can go, okay, well, the second entry is the element of a. So that's the thing that we want to change into a sort of thing ready to feed in. So we have this a dash ready to feed in. And then we want to ready to feed this into f of EAB operating on, we'll leave the h dash we have up here as constant, and we're ready to operate on this a dash. So that makes sense, because what we're basically saying here is that we're ready to feed in this a dash, and once we've got it, we're going to evaluate h dash on a dash, and then we're going to apply this function f to it. And if you think about it, how is this actually going to operate when we do feed in an a dash? Well, it's going to feed it in, then it's going to do h on it. So this is going to give us, when we do EAB h dash on an actual a, when we evaluate it, we're going to get HP2, and then when we do f on that, we're going to get f of HP2. But actually what we've done here is we're ready to do that, but we've actually sort of wrapped this with a lambda. So we've really got, in quotes, FH, because it's ready to take in an A, and then it'll basically just do FH on it. But it'll be FHP2, because of this funny business about converting between 1 times A and A. So that's a bit of intuition about that. So a bit more sort of intuitive stuff is just sort of what's meant. There's a bit of terminology here. We call an arrow R from T times A to B. Sometimes we'll call it a T-indexed family of arrows from A to B. And we can kind of see why we call it that. So consider a point of T. This we're now talking about in general categories. And then we have that, well, we can make this, given this T, which we can think of as a sort of parameter, we then have this sort of arrow from A to B, where we start from A, we sort of have this parameter T, and we leave this A free. We sort of pass this A over here, and then we do R. And obviously, for any different point T of little t of capital T, we get a different arrow. So sort of going over different points, we get these different arrows from A to B. It's just sort of a formalized version of that thing I was saying about calculator buttons at the beginning, really. But yeah, let's now go through this argument again about how f to the power of a works more generally. So I've just been talking about what it does on these names of arrows, but we can think about, what it does on these sort of T-index family of arrows. And I've actually already gone through this, but it's not going to hurt to go through it again. So given an arrow R from T times A to B, and an arrow F from B to C, this is really the core kind of equation that we have, that f of A working on R transpose is f of R transpose. And we can see this by this diagram, which we've already sort of looked at. So we can think of f of A as the unique arrow that makes this diagram commute. But I mean, more sort of more expressively, really, f to the power of A is this. It evaluates, it does the function, and then there's a transpose of it. Okay. And you can actually see that from this square here, actually. Because, I mean, if we just draw like this, we have that this is FEA, comma B. And so this must be the transpose of it, okay? Up at the top right, horizontal blue arrow. Okay then, so anyway, let's just again recap. Why does this formula hold true? Well, this diagram commutes. I mean, this is just a definition of R transpose, and this is just a definition of F to the A. And then, since we have this evaluation arrow here, anything that makes this sort of any arrow from T to the A, well, I mean, if we just compose these two arrows, we get f to the power of A of R transpose times 1. But we could also draw this arrow like this and then say, well, this arrow must be FR transpose times 1A, because well, we can draw this arrow because it has having the property that when we evaluate after this we get f of r, and we see that this arrow here composing these blue arrows has just that property, and there can only be one thing that if we times it by 1 makes an arrow like that. So that means FR transpose is f of a after R transpose. That's what we wanted. And now we can actually use this to give a simpler proof of this formula that we were after before, which is that g to the power of a after f of a is g of f to the power of a. And we can do this really, I suppose the long name of it would be to say when this is what happens when we're operating on generalized elements, okay? Because if you have an arrow, if you can show that it always composing it after any arrow always gives, so say you've got two arrows A and B, and for any x you always get ax equals bx. Well, that means A and B have to be the same. You can see this quite clearly by noting that in that case it has to work for x is equal to id. Okay, so when two arrows always give the same result when we compose them with any particular arrow x, then those arrows must be the same. And that's the basic gist of the argument here. I mean, you could think of x as a sort of generalized element that we're operating on. Okay, a generalized element being an arrow from sort of any object. So we can use this formula we already have. So we have that basically what we're going to show is that g to the power of a, f to the power of a, when we compose that with any arrow, we always get the same result as we do when we compose g after f to the power of a with that arrow. And we can see that because we have this general arrow from t to b to the power of a, and we have g to the power of a, f to the power of a of r is g to the power of a fr transpose. That's just doing this with the formula we just used, and then doing this with it, we get that's g after f after r all transposed, and that's clearly the same as we get from evaluating this. So that shows that g to the power of a, f to the power of a is gf to the power of a.